unveil mystery. Even though we have constructed an intricate and well-founded cosmological model based on a combination of observations, theoretical frameworks, and the rigorous mathematics supporting those theories, the universe still holds mysteries that elude our grasp. There are persistent clues suggesting that the cosmos is not entirely aligning with our models, raising questions about the completeness and accuracy of our understanding. These clues are not mere anomalies. They highlight fundamental discrepancies in our scientific efforts to decode the universe's vast complexity. If you've followed cosmology in recent years, you've likely encountered the term crisis in cosmology. This term encapsulates a series of challenges faced by scientists when attempting to reconcile differing measurements of the universe's properties. The crisis gained prominence when different methods of determining the age and expansion rate of the universe started yielding inconsistent results. To this day, these discrepancies remain unresolved, presenting a profound puzzle to cosmologists. To add to this conundrum, the James Webb Space Telescope, which has delivered groundbreaking observations of the distant universe, has complicated the picture further. Far from clarifying the existing tensions, its findings have intensified the crisis, exposing deeper inconsistencies in our models. While we've created a dedicated video on the crisis in cosmology, linked in the description for a detailed dive, let us briefly revisit the core issues for a clearer understanding. The universe, as we know, is in a state of constant expansion. This concept, central to modern cosmology, is supported by observations showing that galaxies are moving farther away from each other as time progresses. To quantify this expansion, scientists rely on different methods. One prominent approach involves studying the cosmic microwave background, CMB, a faint glow of radiation that represents the earliest light in the universe, dating back to when it was just 380,000 years old. By analyzing the properties of the CMB, researchers calculate the rate at which the universe has been expanding over time, a value termed the Hubble constant. This method provides a perspective rooted in the universe's infancy. However, there is another independent method to estimate the expansion rate. This approach involves examining distant supernovae, which act as standard candles because their intrinsic brightness is well understood. By comparing their true brightness to their observed brightness, we can estimate the expansion rate of the universe at the time those supernovae exploded. This method, which offers a snapshot of the universe's expansion in its more recent history, presents a stark contrast to the results derived from the CMB. The disparity between these two methods has given rise to the Hubble tension, a fundamental issue that encapsulates the growing uncertainty in our understanding of cosmic expansion. While the Hubble constant is a cornerstone of modern cosmology, the fact that its value varies depending on the method used to measure it points to a deeper problem in our theoretical framework. This mismatch has become a focal point of scientific debate, prompting intense scrutiny and a reevaluation of long-held assumptions. Yet the Hubble tension is no longer the sole crisis in cosmology. A new, equally perplexing issue has emerged, a cousin to the original crisis, as some call it. This new challenge further highlights the limitations of our current models, forcing scientists to confront the possibility that our understanding of the universe may be more incomplete than previously thought. For those who have dedicated their lives to developing theories about the universe, the emergence of such crises can be both unsettling and invigorating. Personally, I find this challenge to be an essential part of scientific progress. Science thrives on questioning assumptions, revisiting established ideas, and pushing the boundaries of our knowledge. The discomfort that comes with such questioning is a small price to pay for the breakthroughs that ultimately result. That's why I welcome these challenges. They represent opportunities to advance our understanding. Welcome to Unveil Mystery, your space to explore, question, and engage with the mysteries of the cosmos. When you look up at the night sky from a location free from the interference of city lights, you are greeted by a breathtaking view of countless stars. These celestial bodies, scattered across the vastness of space, tell a story of the universe's immensity and diversity. Amid this cosmic panorama, you may also notice the Andromeda Galaxy, a faint smudge patch of light that stands out among the stars. This distant galaxy, our closest galactic neighbor, is a reminder that the universe is filled not only with stars but also with galaxies, clusters, and other massive structures. Yet, an important question arises. How much of the universe do these objects actually occupy? In simpler terms, how much matter exists in the cosmos, and how is it distributed? While this question might appear straightforward, its answer is anything but simple. Modern cosmological observations are plagued by disagreements and inconsistencies when it comes to determining how matter is spread across the universe in its current state. These disagreements have given rise to what is now known as the S8 tension. This term refers to a specific discrepancy in measurements of the universe's lumpiness, or the way matter clusters together. To help visualize this, imagine the universe as a giant cosmic puzzle with matter scattered like puzzle pieces throughout space. Scientists aim to understand how these pieces are arranged and how they clump together to form the large-scale structures we observe. There are two primary methods for measuring this. The first involves studying low redshift observations, particularly through the phenomenon of weak gravitational lensing. Gravitational lensing occurs when massive objects, such as black holes or galaxies, bend and distort the light from more distant objects. This bending acts as a cosmic magnifying glass, allowing scientists to infer details about the distribution of matter. The second method relies on predictions from the Standard Model of Cosmology, which uses data from the CMB to estimate the clustering of matter. However, the results obtained from these two approaches do not align, creating a new layer of complexity in our understanding of the universe. The S8 tension has thus become a critical area of focus in cosmology, highlighting yet another aspect of the universe that defies easy explanation. To address these challenges, astronomers have turned to cutting-edge technology, utilizing one of the world's most powerful supercomputers to simulate the largest cosmological models ever created. This ambitious effort, requiring over 50 million hours of computing time distributed across 30,000 processors, was carried out on the Draco 8 supercomputer at Durham University in the UK. The project, aptly named FLAMINGO, a complex acronym for Full Hydrodynamic Large-Scale Structure Simulations with All-Sky Mapping for the Interpretation of Next-Generation Observations, represents a groundbreaking leap in cosmological research. Unlike earlier simulations that focused exclusively on dark matter, FLAMINGO incorporates both dark matter and ordinary, baryonic, matter. This inclusion accounts for phenomena such as galactic winds, the effects of supermassive black holes, and other factors that influence the distribution of matter on smaller scales. Despite its sophistication, the FLAMINGO simulations failed to resolve the S8 tension. In fact, they revealed additional discrepancies, such as contradictions with observational data from the James Webb Space Telescope. For instance, while the Standard Model predicts that galaxies should be 7% more clustered than they are observed to be, the FLAMINGO simulations only reduced this discrepancy to 5%, leaving key questions unanswered. These challenges, rather than being setbacks, are opportunities for growth. Science advances through such moments of crisis as they force us to re-examine our models, refine our theories, and explore new possibilities. The universe is telling us something profound, and it's up to us to decipher its message. A major shift in cosmological understanding is on the horizon, and it's an exciting time to be part of this journey. What are your thoughts on these developments? Share your insights in the comments below, and don't forget to subscribe to Unveil Mystery for more explorations of cosmic mysteries. If you enjoy our content, consider supporting us through channel membership or by buying a cup of coffee. Until next time, this is Unveil Mystery.